Hi, everyone. Today I'll be talking about some of the work that we're doing on bringing AI to the physical world. So in terms of where the physical world and where physical AI is at right now, is that it's really challenging to actually try to truly solve a robotics application and truly bring a robot to kind of an end product. And the reason why this is really hard is that if you want to do this, you essentially need to build an entire company around that downstream application. One company for warehouse logistics, a different company for wet lab automation, yet another company for robots cooking in kitchens, and so forth. And when you build this company, you need to make new hardware, you need to develop custom software for that hardware, design movement patterns for the application, handle edge cases, and so on. And you have to do all of this from scratch. And as a result, actually bringing robots into the physical world intelligently is really, really hard. And this is the problem that the company that I co-founded, Physical Intelligence, is trying to solve. And in particular, our goal is to be able to develop a general purpose model that can enable any robot to do any task. And our core thesis is that doing this may actually be better and easier than trying to develop purpose-built models for a given application. And this kind of follows from the trends that we've seen in language models where, for example, you no longer use a purpose-built for drafting emails or translating text, and instead, the general model that's trained on more data works better. Essentially, what we're aiming to do is trying to bring intelligence to the physical world, unlike companies that are focusing more on the digital world. So how do we do this? If we were to take lessons from language models, perhaps we would kind of think about how scale is an important ingredient for accomplishing this goal. And potentially a conclusion we might make is that scale is the most important ingredient for trying to tackle this problem. Let's say that this conclusion was true. If we said that this conclusion is true, then we would, for example, consider data from industrial automation. The data from industrial automation we can get at massive scale, but it's going to really lack diverse behaviors. It's not going to teach us how to, for example, cook meals, bag groceries, and build other kinds of products. Instead, maybe we could look to data from YouTube. This is also something that would have massive scale, but there's a really significant embodiment gap between, for example, the way that people do things and the way that robots might do things. And for example, even us as humans can't learn how to play tennis as an expert by watching videos of Roger Federer play tennis. And lastly, we could also look potentially at data from simulation. And this is something we could also get at a really massive scale, but is going to lack the realism, both in terms of the physics and the graphics of real-world data. And so kind of the kind of takeaway or the point that I'm trying to make here is that scale is really important and necessary for trying to develop these general purpose models, but they're subordinate to actually solving the real problem. And the kind of approach that we're betting on at Physical Intelligence is basically what's worked in other areas of AI, which is to scale up real data collected on real robots. And we can start to get this sort of real data through teleoperation. And here's an example video of Kyler in the background. He's using these leader-arm teleop devices to control the robot, in this case, to light a match and light a candle. So this is the kind of data that we're starting to collect and can allow us to start to bootstrap models for physical intelligence. And what I'll talk about today is some of our results and kind of where the state of the field is at in terms of building this physical AI. And specifically results with large-scale real robot data, at least by today's robot standards, and still somewhat smaller scale than what we see in the world of language models, for example. And so specifically, I'll talk about, can robots succeed in places they've never been in before? Can they respond to open-ended prompts and interjections? And what remain of some of the open problems in the field? So to set the stage, previously, actually almost 1 year ago to this date, we recorded this video. This is a video of our first model, which we called Pi0, and we trained it to fold laundry. So in this video, the robot is unloading the dryer, unloading 5 items, and then folding those 5 items, fully autonomously being controlled by a single neural network to accomplish the kind of full long horizon task. The model isn't perfect, so here it's making some mistakes, kind of misgrasping quite a bit, but it's able to kind of autonomously recover from its mistakes and complete what's arguably, actually in my mind, still one of the most impressive things I've ever seen a robot accomplish in the real world. And one of the things that was cool about some of our work here is that nothing in the recipe was actually specific to folding laundry. We can actually take the same recipe and take the same base Pi0 model and fine-tune it to different use cases, like in this case, cleaning up a table, or controlling a completely different robot to scoop coffee beans into a coffee grinder, to being able to construct these cardboard boxes, and lastly, being able to actually autonomously light a match and light a candle. So this is where kind of we started off about a year ago, and one of the big limitations with these is that we were collecting data in the particular environment that you see. And as a result, when we were kind of fine-tuning these models on the data from that environment, the robot didn't effectively generalize to new environments and was even brittle to changes in the environment that it was in before. And so that kind of wanted us to try to tackle this problem of enabling robots to succeed in places they had never been in before. And as a concrete example, say that we dropped a robot in a home that it's never been in before, and we wanted it to, for example, tidy a kitchen. This requires being able to interact with new objects, interact with new furniture, handle varying lighting conditions, handling a different layout of the room. And it's really challenging because this single neural network model needs to implicitly be able to interpret language commands and figure out how they connect to the novel room layout, be able to decide how to act from raw images of different objects, furniture, and lighting, and also be able to generalize its physical actions to new objects, new countertop types, and so forth. And so, for example, if the height of the counter is different, it needs to adjust actually the kind of where it's moving its joint angles, or depending on the shape of the cabinet handles, it actually will need to adjust kind of how it's orienting its gripper. Essentially, it needs to be able to generalize across language, vision, and action modalities all at the same time in order to be able to do something, in some ways, fairly basic thing of tidying a kitchen it hasn't been in before. So quite challenging. When we approached this problem, we started by collecting large real-world data. And specifically, we collected data in diverse homes across San Francisco, as well as mock kitchens and mock bedrooms that we constructed. And the kind of overall data set covered more than 100 different unique rooms, with the goal of being able to generalize to a new home. Now, we took this mobile manipulation data of kind of tidying kitchens and bedrooms, and we combined it with all the other data that we had collected previously, and also collected data of static robot arms in diverse homes. And the complete data mixture contained diverse mobile manipulation data, both of low-level action prediction and high-level command prediction. But we combined this with diverse data from static robots, basically robot arms mounted to tables. We combined it with data that was previously collected in more laboratory environments with a variety of different robot platforms, as well as data from the web and high-level instructional data of how to accomplish different tasks. And one point I'd like to emphasize in terms of this overall data mixture is that the mobile manipulation data that we collected in homes actually only constitutes 2.4% of the pre-training mix. And what this suggests is that we're able to spin up a new task and a new robot without redoing all of the data collection that we have done previously. We can actually sort of like spin up a new application with much less effort. And this is kind of the power of these sorts of generalist models. Now, this isn't without any further challenges. One of the challenges that we ran into with the Pi0 model is that sometimes it ignores language instructions. And so, for example, here's a video where I told it to pick up the cutting board. The robot dutifully ignores me and decides to pick up the plate instead, then tell it to put the plate in the sink. I ask it to pick up the cutting board again, and it decides that it's going to ignore me again and pick up the pink plate instead. I tell it to then put it in the sink. I ask it to pick up the cutting board again. It tries to drive away, and then eventually kind of obeys and decides to pick up the cutting board. And we were trying to figure out how to solve this problem of ignoring language instructions. And one idea that we have is that existing vision language models, like open source models, they already know how to recognize language and follow language well. And so maybe we just need to figure out how to preserve the language in those pre-trained models. And so what we did is we modified a choice that we made in the Pi0 architecture And that choice we had previously made was to add this kind of diffusion-based action head for predicting actions. But our hypothesis was that when we're randomly initializing the parameters in this head, it may actually be destroying some of the kind of priors and some of the knowledge in the base open source pre-trained vision language model. And so we modified our design, and we instead kind of during pre-training actually predicted tokenized actions and then stopped the gradient from the diffusion head. And as a result, we're actually able to stay closer and more faithful to the original vision language model with the hope of being able to improve language following. And we found that with this sort of kind of pre-training with discretized actions and post-training with diffusion with this stop gradient allowed us to train 4 to 5 times faster and also led to far better language following, 80% follow rate versus 20% in our experiments. So this seemed like a big win, and when we combine this recipe with the diverse data that I talked about before, we were able to drop robots into environments that they had never been in before. This is kind of a home that we rented. We asked it to do things like close the cabinet, put the dishes in the sink, clean the spill. And the robot was able to generalize across all of the 3 modalities like I mentioned before in order to successfully control the joints of the robot, control the wheels of the robot in order to accomplish the task. Now, of course, because this is a new home, we can also drop it into other homes as well. So here's the last part of the task where it's cleaning up the spill. We then packed up the robot and brought it to a completely different home in San Francisco. So the robot is, here you can see we're packing it up, bringing it to a different home. Now Laura, in this case, is going to ask the robot to clean a bedroom. And with the same model, it's able to also generalize to a completely new bedroom in this case and tidy it up by putting the laundry into the basket, throwing away some tissues on the ground, and tidying the bed by putting the pillow at the top and adjusting the comforter. Cool. And we did further testing in other environments as well. We did a number of quantitative evaluations of this model, and there was a few kind of interesting tidbits that we found. The first is that if you compare our recipe in yellow to excluding web data or excluding, specifically if you exclude data from other robots, from static robots, in lab environments, in diverse environments, or all of the static robot data, we saw substantially worse performance compared to if we only used the mobile manipulation data. And this suggests that kind of the base generalist model is really contributing to actually being able to get good performance in these held out environments. And then we also found that as we increased the number of locations represented in our training data, we saw increased performance on the robot. And we actually even saw that when we moved to around 100 environments in the training environment, we were able to close the generalization gap and get near the performance of actually if we had collected data in that target environment. I should also mention that the success rate is not perfect, and there's a lot of open challenges, and so we see a number of different failure modes, and I'll highlight a couple of those failure modes here. Here's one example where we tell it to put the items in the drawer. The robot puts the oven mitt in the drawer, decides that this is good enough, and drives away. In this case, it's trying to put the clothes in the laundry basket. It actually drives over the shirt and really struggles to recover, and eventually put and isn't able to successfully put it into the laundry basket. In this case, it's trying to put all 4 dishes into the sink, and it's able to do the first 3 objects, but struggles to pick up the cutting board because it's quite thin. Some of the times it succeeds, some of the times it isn't able to pick up thin objects. And then lastly, my favorite example, its goal is to put the spatula into the drawer. It decides that this looks kind of like a drawer, and thinks about putting it into the oven. It doesn't actually quite make it in there, but another failure mode. There's also challenges with regard to speed, long horizon planning, and partial observability. So the takeaway for this part is that with diverse data and with a good pre-training and post-training recipe, we can allow robots and physical AI systems to actually follow a variety of instructions in completely new homes and completely new environments. Now, moving to the next part, one other limitation here is that the set of instructions we can ask the robot is limited. And ideally, we could move towards a world where we could actually, kind of just like we prompt ChatGPT, we could actually prompt robots to follow a variety of different instructions and a variety of different kind of use cases that we might want the robot to do. Now, to do this, we've explored using hierarchical models where we have a high-level vision language model and a low-level vision language action model. And the role of the high-level model is to interpret kind of an open-ended prompt and then translate that into a specific command for the low-level model to follow. So for example, if the goal is to kind of follow some prompt about making a sandwich under various user constraints, then the high-level model would then translate that into what the low-level model should do at the very next step, like pick up one slice of bread. And then the low-level model, its goal is to actually execute that atomic command and control the joints of the robot to accomplish the task. Now, this doesn't on its own allow us to handle open-ended language. And in particular, we need data for training the high-level model. And one thing that's really challenging is that collecting diverse human-robot interaction data is really hard to scale because it means that not only do we need to collect the robot data, but we need to collect all sorts of human interactions that might kind of intersect with different ways the robot might perform the task. One idea we had here is that instead, language models actually know quite a bit about how humans might be interacting with the robot, and so we can actually augment robot data with language models to synthetically create lots of different prompts and scenarios that robots might encounter. So for example, say that the robot is about to pick up a Kit Kat. We can then ask a language model, what is a prompt that could have led to this situation? For example, a prompt like, hi robot, can you get me something chocolatey? And then use these prompts that are synthetically generated as training data for our high-level model so they can follow a variety of open-ended prompts. And with this approach, we can train the model to follow a variety of different prompts and interjections. So in this case, we asked the robot, can you make me a ham and cheese sandwich? This is a pretty complicated task. The high-level model breaks down that prompt into kind of low-level steps, like pick up one slice of whole wheat bread, put it on the chopping board, pick up one slice of cheddar cheese, and so forth. And we're able to actually translate that high-level prompt into actually actions on the robot. We can also look at a much more complicated prompt, like, can you make me a vegan sandwich? I don't like pickles, though. And the robot can kind of interpret that, reason through that prompt, and create a sandwich that has lettuce and tomatoes on it. It can also handle interjections. So for example, in the left case, the user also asked for more pickles, and the robot was able to add that in the middle of execution. It'll then kind of be able to follow different prompts and get very different behaviors. So by default, typically the robot will clean up the whole table in a situation that looks something like this. But we can ask it instead to clean up only the trash but not the dishes. And this gives us a degree of controllability over the robot's behavior, where it will then kind of indeed follow the user's instruction. And then lastly, we can look at situated corrections. So here, the robot picks up a Kit Kat, and the person asks, get me something sweet that's not in the basket. And then the robot can reason through the fact that it just picked up a Kit Kat, kind of situated in its current environment, think through what sweet things are in front of it, and decide that it will get some Skittles for the user. Now, you might be wondering, like, maybe some existing foundation models off the shelf might be able to already do this sort of reasoning of translating prompts into low-level robot instructions. And generally, what we've found with these sorts of models with GPT-4o, but also more recent models like GPT-5, Gemini 2.5, and so forth, is that they really struggle to kind of have the visual understanding and the kind of situated reasoning that pertains to robotics. And we see quantitatively that these models often lag behind the models that we're developing in-house. Cool. So we've seen how robots can succeed in new places that they've never been in before and handle a variety of open-ended prompts and interjections. What I'd like to talk about at the end, actually, sorry, before I talk about that, I'll also mention that both Pi0 and Pi05 are actually open source models, and so you can play with them. I've also had a lot of fun seeing what different people have used these models for, and it's actually gone quite far beyond my expectations. We've seen people kind of fine-tune these models, not just to robots that look like these robots, but also to surgical robots, to quadcopters, and it seems like these models are quite general because we've trained them on a variety of robots in a variety of environments. Now, what remains as open problems in physical AI? One of the things I'd like to highlight is that there's a lot of open challenges, and this problem is far from solved. For example, one of the things you might be surprised to learn is that the state-of-the-art models in the realm of robotics typically don't have any memory. And this means that if you apply these models to situations that require memory, like dusting a shelf and then replacing the objects, the robot will forget that it had already dust the shelves and kind of then dust them again because it doesn't have any memory of what it did before. And so in some of the research in my lab at Stanford, we've been kind of studying these kinds of bleeding edge problems and for example, have developed a model that can have this sort of memory by retrieving frames efficiently and completes tasks like this. Another really hard challenge is completing tasks at human speeds. A lot of the videos that I showed before are sped up by varying factors. And we need to think through ways to enable these robots to complete tasks at human speeds or faster, potentially through more intuitive interfaces, allowing us to fold shorts in 6 seconds, or potentially through post-training with reinforcement learning, which has allowed us to also be able to really efficiently complete a task like pouring almonds. And then lastly, if we want to actually deploy these robots, it's really important for them to not just achieve 80% success rate, but to get to even higher percentage success rate. And we've been studying different reinforcement learning algorithms that allow us to get to really high reliability. And we've also seen other open source work by NVIDIA, for example, that have taken the Pi0 model and fine-tuned it for kind of precise GPU insertion tasks, in this case, with really high reliability. So to kind of summarize what I've talked about today, first, these general models, I think we've seen that they often are more successful than specialists. And I think that this will continue to be the case in physical AI applications and robotics. I also think that large-scale real-world data is going to be necessary, but not sufficient for solving this physical intelligence problem. And that ultimately we need more research before we'll actually be seeing these robots deployed in real-world situations. We're also hiring for a number of a variety of different roles, and we have really interesting technical problems, both across hardware, software, research, operations, and so forth. Whenever you're dealing with robots, things get pretty complicated. Yeah, and I'll end there. Thank you.